Verification Corner!
Hello and welcome to Verification Corner. I'm Rustan Leino. Today we're going to have fun with loop invariants and deriving a program from its specification, something I first learned from Wim Feyen. Alright, before we get into the actual demo on the computer, let me show you some things on the whiteboard in order for it to make sense. Okay, when we reason about the program, we think of a program text, let's say S, and we're going to think about what program state S begins in and which program state S ends in. And we're going to write those as P and Q. I will write P and Q as the beginning and ending program state. And it's typical to surround these in curly braces to show that they're not part of the actual program text. So what we have here is what's called a Hoare triple, named after Tony Hoare. It says, if you start the program S in a state satisfying P, then it will terminate in a state satisfying Q. Now, there are different variations of Hoare triples that worry about termination in different ways and whether or not the program can go wrong in the middle and so forth. We won't have to worry about that in this demo. But this is a general form to reason about the program. So now let me show you two program statements that we will need for the demo. The assignment statement and the loop. All right, for the assignment statement, something like X gets E. If you want that program statement to end in a state satisfying Q, where Q is some condition on the program state, then the state that you want to start this program in would be the same state Q, but where we have replaced the variable X with the expression E. Let me give you some examples. Okay, suppose that we have the program statement X gets Y. And suppose that we want this program statement to end in a state satisfying X is equal to 10. All right, what is the initial state that we need to start in? Well, the rule says just take the postcondition and replace the variable that's being assigned with the right-hand side. So we replace the X by the Y, and therefore we get, as the program state, in the initial state, Y is 10. So this Hoare triple says that if you start the program in the states where Y is 10, and we don't know anything in particular about X, and then you execute the assignment statement, you will end up in a state where X is 10. Okay, easy enough. Let me show you a couple more examples. If we have the statement X is incremented by 1, and we want that program statement to end in a state where X is at most 10. Well, the rule says again that when we compute the pre-state that we need is that we replace the X by the right-hand side, which here is X plus 1. So we're going to get that X plus 1 is at most 10. Well, I can rewrite that to simply X is strictly less than 10. Okay, that was that one. Let me give you one more. Suppose that we have a more complicated assignment statement. Maybe something like X gets 3 times X plus 2 times Y. And suppose that we want this statement to satisfy something like X squared is equal to 81, perhaps. All right, what do we need in the initial state? Well, there's no thinking involved here. Just replace the variable X with the right-hand side of the assignment. And then we will get 3 times X plus 2Y squared is equal to 81, and I don't have room. All right, so, and of course you can simplify this expression in various ways, but the fact that this is so simple and there's no thinking involved, you just do the replacement, should make you think that the computer can indeed do this for you. Okay, so that's the assignment statement. Now let's look at the loop, which is more interesting. Okay, so a loop looks like this. While, and let me write it in this form, while b do s. And suppose that we start that loop in a state satisfying p, and suppose that we end it in a state satisfying q. What is required for the loop to satisfy this Hoare triple? Well, what you need to do with loops is that you need to introduce a loop invariant. So a loop invariant is something that holds on every iteration of a loop. That is, at the very top of every loop iteration, including the first one and the very last one. Let's call it loop invariant j. So in order to prove this Hoare triple, that is, in order to reason about the loop, you need to come up with some loop invariant, and the loop invariant needs to be something that holds initially. That is, we want that the pre-state that we have should satisfy the loop invariant. Let's call it j. So p implies j is the formula we would prove. Then we would want to show that the loop invariant is something that holds every time through the loop, which is something sort of like the induction hypothesis when you prove mathematical theorems using induction. So let me write that as follows. If we start in a program state where the invariant j holds and where also the loop guard holds, then we execute the program statement s, which is the body of the loop, and then we want to prove that we end up in j still. That is, that the loop invariant continues to hold. And we need one more thing, and that is that if we start in a program state where the loop invariant holds, that is, we're at the beginning of a loop iteration, and where the loop guard does not hold, so we have not b, the negation of b, then we want that to be strong enough that will satisfy, that q will hold. So, in summary, to reason about the loop, if you want the loop to terminate in a state satisfying q, what you need to do is you need to come up with a loop invariant, and that loop invariant needs to be something that should hold just before the loop. It needs to be something that is maintained by the loop, and it must be something that is strong enough so that it and the negation of the loop guard will give you the postcondition that you want. All right, that's enough for the whiteboard. Now let's go to the computer and see these things in action. All right, so here we are at the computer. What we're going to do now is apply the loop invariants that we saw, and we're going to actually make the tools help us in constructing our program. So I'm sitting here in Visual Studio, and the language that we're seeing on the screen is Spec Sharp, which is a superset of C Sharp. It's a research language that we have constructed here in the RISE group at Microsoft Research.
And it's important to say that Spec Sharp is on Codeplex if you want to.
Oh yes, that's
mess
right.
around
Spec
with
Sharp is on Codeplex, so you can get the tools, you can get the sources even, specsharp.codeplex.com. Okay, so the little demo I'm going to give is that of computing the cubes of the first n natural numbers here. So we can see in the program a method cubes, which takes an array of integers, and we're going to fill up that array with cubes. So the way we're going to do that is, first I'm going to write the postcondition, which is going to say what this piece of code is actually going to do. And the postcondition in this case is more complicated than we often write things in code contracts or even in Spec Sharp, because I'm going to use a quantifier, but you'll catch on, I'm sure. So we're going to say that for all I in the range from 0 up to, but not including, the length of the array, a sub I is going to be equal to I cubed afterwards. So that's what we're going to compute. So in other words, we're going to set each one of the elements of the array to the cube of the index of that array, of that element. But I need to do something else. I need to also say that this method gets to modify any element of the array in the modifies clause. I won't be talking more about modifies clauses here, but come back to verification corner for other episodes on modifies clauses. Okay, so what we're going to do is we have to do this by loop, of course. And so I'll write the loop here, and I'm just going to write a skeleton a little bit here of the loop. And we know that to reason about the loop, we need to have a loop invariant. So SpecSharp allows you to write down a loop invariant, and so I'm just going to write the loop invariant here. And now the question is, what is that loop invariant going to be? Well, there are several tricks for coming up with a loop invariant if you start from the post condition. And so what I'm going to do is I'm going to copy the post condition, and I'm copying it to the invariant, but I'm going to change it a little bit. I'm going to use what's called replace a constant by a variable, which is a trick that often works when you want to construct a loop invariant. So the constant in this case is going to be the length of the array. So I'm going to replace that by a variable, and I'll call it n. So I will introduce that variable n. So this is something that you would do automatically yourself too. And we're going to loop until loop while the n is less than the length of the array, and afterwards I'm going to increment it. Now, of course, we'd usually write n++, but let me just write n gets m plus 1 here, which is, of course, the same thing. Okay, this is the usual thing that we would write for a loop invariant. That is, we have some loop index that's going to be incremented. And I'm not proving termination here, but it's clear that this loop actually does terminate. And but we're getting a warning. The warning that we're getting here, which we can get by just hovering the mouse over the green squiggly, or if we look here at the bottom of the screen, we can also see the same warnings come up. And the warning is that after the loop iteration, it says that the loop invariant might not hold. And of course, we're not doing anything in the loop to set the elements of the array. So what we're going to do is simply set a sub n to n cubed. And with that, the squiggly goes away. I don't note, by the way, I don't have to touch any buttons or anything. I just type in the program, just like we get little squigglies here for syntax errors. We get little squigglies for the verification errors, and they go away when the verifier is happy. So that's the program. But this would be too easy. So what we're going to do is we're going to complicate things for ourselves a little bit, and we're not going to allow ourselves to use the multiplication operator. So you might now think about whether or not you immediately see how to change this program so that it will still produce that post condition, but without using the multiplication operator. So here's what we're going to do. We're going to apply a wish. So wishing is good. So we're going to wish that we had some other variable that just happened to be equal to the cube of n.
Especially in this time of year.
Especially in this time of year, indeed, which happens to be December. So if we wish for such a variable that is equal to n cubed, then what we can do down here is simply replace the assignment and just set the a sub n to c, because c is going to be n cubed. That seems really nice. But we get these squigglies. So the squiggly here complains that there is no variable called c, so we'll have to introduce that. So let me introduce the variable c, and we need to initialize it somehow. And now you remember from the whiteboard that the invariant that we've introduced must be something that holds initially. So we need to set the variable to something that's going to make the invariant hold initially. And in this case, since n is 0 to begin with, and 0 cubed is 0, so we're just going to set c to 0. And that will satisfy the loop invariant initially. But of course, we also need to maintain it. And you can see here from the message that it says after the loop invariant, after the loop iteration, that invariant might not hold. So we fix that simply by at the end of the loop again, setting c to n cubed. And there we are. The verifier is happy again. But remember, we were trying to avoid using multiplications, and here I'm using it again. So now what I'm going to do is I'm going to use the first thing that we saw on the whiteboard, which is that an assignment, in particular in this case, the assignment to n, if we want c to be equal to, or something to be equal to n cubed afterwards, then the property that matters before the assignment to n is that the same property holds, but with n replaced by n plus 1, because that's what the assignment does. So let me copy this line, and I'll put it just above the assignment here instead. and I will replace all of these with n plus 1s. And then we don't need the line afterwards again. So now what I did was, all I've done is I just moved the assignment to C, and I moved it so that it comes before the variable n instead of afterwards. But we still have the multiplications. Okay, so now you will feel tempted, as I do, to distribute the multiplications here. But we want to make sure that we remember the right form of this expansion. So I'm going to let the tool help me. So I'm going to introduce an assert, and I'm going to copy this expression, and I'm going to say that using the binomial coefficients here, I'm going to say that this is equal to n cubed plus 3n squared plus 3n plus 1. And if I get no complaints, which I don't, then the assert is correct. And in fact, just to check it that nothing fishy is going on here, if I just change the expression a little bit, then we get a complaint here. So I did the right thing. Okay, so we let the tool help us with our math here. Okay, so now if those two things are equal, then I can just use that expression down here in the assignment instead. So let's do that. And I don't need that part, and I don't need the assert either, so let's just get rid of that. That was just to help us a little bit. Okay, so we're not much better off, you might say, but a little bit, because you notice that here we have the expression n cubed, and we have something else, a variable that we wished for, namely c, that is always equal to n cubed on entry to the loop. So what I can do is I can just replace the n cubed here by c. And now we have a little bit fewer multiplications. So that worked really well. So let's just do the same thing again. Wishing was good. So we're going to wish that we had something that stood for this expression. So I copy that, and I will add another invariant, and I will introduce a new variable k that I want to be equal to that thing. And if k is equal to that thing, then I can just replace that expression down here with k. But we get the complaint about k that it doesn't exist, so I will have to introduce it. And what is its initial value going to be? Well, remember that it needs to establish the invariant to begin with. So if n is 0, then it looks like it's going to be, I'll have to set k to 1. And so, by the way, just in case, suppose that we set it to 0, since we often initialize things to 0. Then we'd like to see what happens. Well, then we get the complaint from the checker saying that initially the loop invariant does not hold. So that was wrong. But if I change it to 1, then the initially complaint goes away. And now it complains that we're not maintaining it, which is the next thing to do. Okay, so again, we're going to set k after the loop. We want to maintain it so that it's always equal to this condition. So I'll just copy it down here. But again, we're updating n afterwards, so let's do the same trick again of copying this, and I'll put it just before the assignment as we did before. I'll delete it afterwards, and just before the assignment, remember from the whiteboard that we will need to do the substitution that n is replaced by m plus 1, because n gets m plus 1 is what we do in the assignment down here. Okay, and now we get no complaints again. And now we need to distribute things again. Let me distribute the things within the parentheses here first. Here we get n squared plus 2n plus 1. Means I can erase that part. And okay, and then let's also distribute the 3 times here. So it's going to be 3 times n squared. Here we get 6 times n. And here we get 3. Let's do the same thing here. 3 times n plus, and there we get the 3. Okay, and again, the verifier is happy we've not introduced any errors in the process. And now we're in the same situation again, that we have an invariant. K is equal to that term. And afterwards, we're setting k to something that includes those terms. So here's the 3n cubed, which we have down up here. Here's the 3n, which we have up here. And here's the 1, which we also have up there. So what we can do now is just erase those parts. I'll erase that. I'll erase that. And I will erase that part. And I can now replace that by k plus the other thing, because remember k was equal to that. Okay, so we've made further progress. We're not quite there yet. We have one multiplication left. Let me simplify this, by the way. That's 3 plus 3, that's equal to 6. Okay, but we've had such good luck with wishing, so we will wish once more. So
You
here
have a lot of wish this year.
it's another wish, and it seems hopeful that things will work out. So let's replace that. I'll put m down here. And again, it's complaining that we're wishing for a variable that doesn't yet exist, so we will introduce it. And its initial value, again, n is 0 to begin with, so therefore we want m to be equal to 6. And in this case, we could do the same thing with the update, but in fact, this one is so simple that we can just look at the program and just do the update in our heads. And we can see that if we update n by 1, we have to update m by 6. So that's what I will do over here. Okay, and there we have the program. We have no complaints, which means that the verifier is happy. And the program that we wrote uses only additions, as you can see, and no multiplications. And the loop invariants are established, and in the end we get the postcondition that we had started with. All right, in summary, what we've seen today is loop invariants, and we've seen that you can derive, in some cases, the program from the specifications, from the postcondition, coming up with the loop invariants. This has been Verification Corner. I'm Rustan Leino. Program safely.